If we look at 2 points on this curve and draw aligned segments between them, we can see that as the points get closer together, the line gets closer to the tangent at that point. Let's zoom in on that particular point. The gradient here will be the change in y coordinates, represented by big delta y, over the change in x coordinates, big delta x. Big delta, which looks like a triangle, means big change in. Small delta thus means a small change in. Let's go back to the curve. The point where we need to find the gradient will have its x coordinate as x. Now its y coordinate will be represented as some function of x. So let's write the y coordinate as f of x. The next coordinate along will be a small amount to the right of x. So its x coordinate will be x plus delta x, and its y coordinate will be f of x plus delta x. To find the gradient, we need to take the difference of these y coordinates and divide them by the difference in the x coordinates. The x's at the bottom cancel, leaving us with this. This is the actual definition of a derivative, the gateway to calculus. Anyway, let's go ahead and do a basic kind of function, a function with a power. If we plug this function into the equation, this is what we get. Let's rewrite this and try and expand it. If we take a power of n, of x plus delta x, we will get x to the n as the first term, n times x to the n minus 1 times delta x as the second term, and a few other terms. We get these from binomial expansions. The rest of the terms, though, have a power of delta x which is greater than or equal to 2. Finally, we put the rest of the equation in. The x to the n's cancel out on the top, and the delta x's all get reduced by a power of 1 because of the division. And this leaves us with the first term, n times x to the n minus 1, plus a lot of other terms with a multiple of delta x. But as delta x gets closer and closer to 0, so the line gets closer and closer to the gradient, the rest of the terms go to 0, and this leaves us with just n x to the n minus 1.